And first of all, though, I want to thank the Society for giving me the opportunity to share some of the wonderful results from NASA's New Horizons mission to Pluto and the Kuiper Belt. Let me go back to this opening slide here. It was just under 2.5 years ago that this little spacecraft, shown in the artist representation up here to the upper left, passed just 12,500 kilometers above the surface of Pluto, so that's roughly 7,500 miles, and returned to us a whole new world, something that we could never have imagined. And one example of that is in the background scene here, and I'll be sharing some of these exciting results with you in a few minutes. But before I do that, let me just give you a little bit of background so you can put this in perspective. This is a little cartoon of the solar system with the sun in the center, and all of these white dots represent the Kuiper Belt. This is what we are now calling the solar system's third zone. If you think about the architecture of the solar system dividing into zones, you have the first zone being the terrestrial planet zone, relatively small, rocky planets, Mercury, Venus, Earth, and Mars. You step out into the second zone, the realm of the giant planets, Jupiter, Saturn, Uranus, and Neptune. And now we finally have taken the step into the third zone, something that we didn't even know existed until the early 1990s. And the orbit of Pluto is shown in yellow here. And Pluto itself, of course, was discovered in 1930 by Clyde Tombaugh at the Lowell Observatory in Arizona. But it has always, it stood out like a sore thumb, a real anomaly for over 60 years. Because as you can see from the orbit of Pluto, it's unlike the other planets in the solar system, which have nearly circular orbits around the sun. Pluto's orbit is highly elongated, looks more egg-shaped, with an eccentricity of 0.25. It actually comes inside of Neptune's orbit to about 29 astronomical units from the sun. And for the non-astronomers here, we like to describe distances in the solar system using a unit called astronomical unit, which is the average distance between the sun and the Earth, 93 million miles, about 150 million kilometers. So the Earth is 1 AU from the sun. Neptune is at about 30 AU from the sun. So Pluto actually comes inside of Neptune's orbit at about 29. It did that in 1989, and now it's going back out again. It goes all the way out to 48 AU during its 246-year journey around the sun. So it was completely different than all the other planets in the solar system. And not only that, but you can see the other striking thing about Pluto's orbit is it's tilted by about 17 degrees relative to what they call the ecliptic plane, the plane that contains the sun, the Earth, and Jupiter, and the other planets of the solar system. So it really did stand out like a sore thumb until in the early 1990s, when another object was discovered in that same region of space, and then it just took off exponentially from there, the discovery of new objects. And we're now up to about 2,000 objects in the Kuiper Belt. It's the most populated region of the solar system for everything inside of the solar system, more populous than the asteroid belt. But anyway, in the early in the 1990s, before the Kuiper Belt was even discovered, there was a group of planetary scientists who thought Pluto was worth studying and put together the case for doing a mission to Pluto. And the discovery of the Kuiper Belt really just added extra motivation for doing this, because the discovery of the Kuiper Belt really revolutionized our view of the solar system's formation and evolution. And I don't have time really to go into all the reasons why, but the planets haven't always been where they are now. There's been a huge amount of radial migration of the giant planets in the solar system. Jupiter is now at 5 astronomical units away. We now think that it, at one point early in the solar system's formation, came in almost as close as Mars and then went back out again. That set up all kinds of unstable effects. Things were just mixed up like crazy, and we now believe that story is true, though, because in order to produce the architecture of the solar system that we see today, you needed to have that kind of radial migration. So the first chance to actually examine objects in this new region of the solar system, the Kuiper belt, came with the New Horizons mission, which was launched in January of 2006. But Pluto is way out there. It's more than 3 billion miles away, and it takes a long time to get there. So we didn't get there until the spacecraft didn't arrive until July of 2015, about 9.5 years, that it took. And it's continuing on deeper into the Kuiper belt. As I was mentioning before, it's a relatively small spacecraft, but it had to be small in order to be able to get it to Pluto in a reasonable amount of time. And because it's so far away from the sun, you couldn't fly solar panels. We were nuclear powered, actually. The radioactive decay of uranium-238 that causes a lot of heat, that drives thermocouples, that drives the electricity that powers the New Horizons spacecraft. When we launched the spacecraft, the RTG, the radioisotope thermoelectric generator, was generating about 240 watts. By the time we got to Pluto, that was down to about 195 to 200 watts. But that was sufficient. We had to build instruments that were lightweight and very energy efficient in order to be able to do this mission. And I don't have time to go through all of the different instruments, but suffice it to say, they're highly capable, but they're also highly energy efficient. All of the instruments turned on all at once draw only 30 watts. Okay, so for the electricity that you require for your nightlight in your bathroom, you can turn on and run all of the New Horizons instruments. But we have color camera, high-resolution camera, infrared spectral imager, ultraviolet spectral imager, all of these things so that we can do the reconnaissance, the very first reconnaissance of Pluto and its satellites. The spacecraft itself is roughly the size of a baby grand piano. The largest single structure is the radio dish there, which is 2.1 meters, so about 6.9 feet across. Okay, so if you're in the space science business, I have to show you this.
3, 2, 1. We have ignition and liftoff of NASA's New Horizons spacecraft on a decade-long voyage to visit the planet Pluto and then beyond. Plus 15 seconds. Everything continues to look good as the Atlas V vehicle climbs away from Florida's east coast. The 5 solid rocket strap-on boosters are burning just fine, sending the New Horizons spacecraft on its way to the very edge of our solar system.
The weather was cooperated. We were over the Indian Ocean in 40 minutes, 45 minutes. We reached the orbit of the moon. The spacecraft reached the orbit of the moon in only 9 hours. So when I went out to the hotel, out on the balcony of the hotel room where I was staying that night, January the 19th at 11 p.m., just 9 hours after the launch, and to see the beautiful full moon and to think the spacecraft had already crossed the orbit of the moon. And it used to take takes the Apollo astronauts 3 days to get to the moon. This was the fastest spacecraft ever to leave the Earth, and it was on a beeline towards Pluto. But in fact, we wanted to launch in this particular window in January because there was an alignment with Jupiter, and when the New Horizons spacecraft flew just behind Jupiter, it stole some momentum from Jupiter's gravity and accelerated the spacecraft by about 20% and cut more than 3 years off of the travel time to get to Pluto. So, I mean, even then it took 9.5 years, but we were happy that we didn't have to wait even longer. We'd still be, still wouldn't have reached there by now. And we got some great, actually, the other benefit of flying by Jupiter, besides getting that gravity assist, is it gave us a rehearsal, basically, of a planetary flyby with this mission. It was actually a stress test. We did more observations at Jupiter almost than we did at Pluto. But we flew by Pluto, and look at this. We got the best view of a extraterrestrial volcano ever obtained. This is the innermost Galilean satellite of Jupiter, Io, the most volcanic object in the solar system. Its insides are just churned away by the gravity of massive Jupiter, 320 times as massive as the Earth. But we had this one volcano. We just happened to fly by when Tavashtar was erupting and got this beautiful plumes of material going up thousands of kilometers above the surface and falling back down. We could actually watch the particles, the trajectories, and look in detail at the volcanic eruption. This is the geometry of the flyby. I don't have time to go into this in too much detail, but Pluto has a really weird geometry. Its pole is actually, if the sun is over there, it's pointing a little bit below the ecliptic plane and off to the side. And Pluto also has 5 satellites, and so all in the same, rotating around Pluto in the same plane. So it's like we're going through a bullseye. And this shows the trajectory of the New Horizons spacecraft going from right to left every 10 minutes as we penetrated through the system. And we actually had the spacecraft fly through the shadow of both Pluto and Charon, because we had this very interesting experiment to look back at the Earth and the Sun while the spacecraft passed into Earth's shadow, and we radiated power up the radio signal from the Deep Space Network, the NASA's Deep Space Network, up to the spacecraft and watched the phase change of the radio waves as they passed through Pluto's atmosphere that allowed us to basically measure the pressure and temperature as a function of height above the surface of Pluto with that experiment. And at the same time, because the Earth and the Sun are only a couple of degrees apart as viewed from Pluto, we could also use the ultraviolet spectrograph to sound the upper atmosphere and measure the molecular composition of the upper atmosphere using the Sun as a light source and looking at the absorption of molecules in the upper atmosphere of Pluto. Very high-level statement of the scientific objectives. What do these objects look like when you finally get there and get close? What is their surface composition? And Pluto does have an atmosphere. In fact, it's remarkably similar to Earth's atmosphere. It's mostly molecular nitrogen, except about 100,000 times less dense at the surface. Okay, just one more thing before I get into the results from the mission itself. To the left is the best image ever taken from Earth of the Pluto system using the best available optical observatory ever built, the Hubble Space Telescope. This is a 100-minute exposure, and it shows you how we just barely detect all of the satellites, the small satellites. Styx was the last one to be detected. And we found out that Pluto wasn't just, when the mission was approved, it was 2 objects, Pluto and Charon, and now we've added 4 more. So this is the best Hubble image of Pluto. There it is to the same scale from New Horizons. So this is why we go there. This is why we do space missions, in order to go from here to here. And I can't tell you how many of my colleagues in the planetary science community have spent decades looking at those other kinds of images and squeezing out a lot of information, but it just doesn't compare. I mean, you could never get to this point by remote observations. So Pluto, and some of you may recognize the beautiful, the notorious heart of Pluto. It's in the heart-shaped region here. That is a giant. This is a giant sheet of molecular nitrogen ice. We have this left ventricle here. Is really just this. It's really the lifeblood of Pluto. Molecular nitrogen is an extremely volatile ice, and we're near just below the triple point of molecular nitrogen. Pluto is about minus 390 degrees Fahrenheit. Extremely cold, but molecular nitrogen ice is basically active at those very cold temperatures. And because you have this giant sheet, we think it was produced during a giant impact, created a basin, and they got filled in by the molecular nitrogen. And the fact that you have this molecular nitrogen ice sheet here, and the sublimation and condensation cycles that took place over the course of the age of the solar system, has produced this remarkably diverse geography around on Pluto. And when you look at what I showed you before, the previous picture was in natural color if your eyes were there and looking at Pluto. But we have we can do better than the eye, and we have color filters which allow us to squeeze out compositional information by looking at different colors, and that's what we show here. I mean, it's not a cheat. This is, the different colors are really are telling you that there's different compositions, in these different regions. Now, the North Pole of Pluto is about here, and you see this really dark red equatorial band. These are complex hydrocarbons. We've been calling them in the planetary community tholins. You have all kinds of simple hydrocarbons in Pluto's atmosphere. You get ultraviolet light photolyzing that stuff. You get cosmic rays and solar wind. And we have these precipitates that form in the atmosphere and then rain down on the surface of Pluto and become this gunk. We're not sure chemically what it is, but we produce things in the lab that have the properties of the same properties, and it's just very complex hydrocarbons along this region. And then all kinds of other stuff. Now, you take that picture, all of the images that were taken by the New Horizons spacecraft, we've made them public. The whole world can see them. And there's been these remarkable people out there who've spliced together some of the images of Pluto into these beautiful movies, and I'm going to show you one now from Roman Karchenko. He's basically a music producer, but he loves space science. He loves, what we produced in the New Horizons mission, and he produced this incredible movie that I just wanted you to see here. Let me blow it up for you. These are real images taken from the spacecraft that he spliced together, moving from the bottom of Sputnik Planitia, that molecular nitrogen ice sheet, and then moving around as if you're on an airplane flying over it, okay? And what you see is, you see a very ancient region with all of these craters going back 4 billion years. These are what we're just flying over there, the Aladrisi Mountains. These are giant blocks of water ice that are floating in the nitrogen ice. And you go up and see that geometrical pattern. There's actually convective flow that's going up and down like a lava lamp. You get heating from below that heats up the molecular nitrogen ice. It rises and then falls and produces this geometrical pattern that you see here. The ice is actually flowing. But just this incredible view from Roman, just a wonderful thing that he has shown here. Let me go back to the PowerPoint. And just show you some close-up views. You can see what looks like flow around barriers here. This is like it's almost like a water ice glacier on the Earth, but it's a nitrogen ice glacier on Pluto, flowing maybe a couple of centimeters, over decades. And you see the geometrical pattern there. Let me just quickly go around. We got just incredible detail, these pits, sublimation pits, and you get these extremely flat regions. In that Sputnik Planitia area, we could not find a single crater. That indicates that's very young, geologically speaking. The upper limit is a few million years. It might even be, basically, current times. And then, you get these rugged highlands. You've got mountains on Pluto, water ice mountains that are as high as the Rockies in the United States. That's what these are here, 4 to 5 kilometers high. And there's even evidence that something is oozing out of the surface. This is right here. If you look over here, this red stuff coming out, we think is emerging from depth in Pluto's surface. And here is, once again, another view. Look at the scale here. These are massive features, bigger than anywhere else we've seen in the solar system, actually, for this kind of geography. And there's a little pool, but not so little, it's probably 20 to 30 kilometers across, nitrogen that hasn't run off yet. And then just another view, a color view, you can actually see layering in the rocks here, so we can date when things are happening. And then we were calling this the snakeskin region on Pluto. These are now we're calling it bladed terrain. These are methane ice features that are aligned north-south, and It's high enough that methane condenses out, but molecular nitrogen doesn't. So it's rich in methane. And then there's that dark red material that I was talking about before. And here's going back to that image, and this little figure up here in the right shows you where we're talking about relative to the heart of Pluto. And when I saw this, I first saw this in Labor Day weekend in 2015, a couple of months after the New Horizons flyby, because that's when we started systematically sending down the data. And I couldn't believe this. I was just blown away that weekend, and the whole science team was abuzz. I mean, just look at this. You've got here's Sputnik Planitia. The sun is into the page here. You're looking at this, and you see these mountains, and you see the shadows. But the other remarkable thing that you see is look on the horizon. This is Pluto's atmosphere, which is hazy. You have at least 20 layers of haze, different layers of haze in Pluto's atmosphere. And this is really something that we, hadn't really expected and saw. I don't really have time. This is the geometry drawn a little bit more accurately. This just shows you that experiment that I was telling you about. As Pluto flew behind into the as the spacecraft flew behind Pluto into Pluto's shadow and looked at the radio signal from the Earth and looked at the sunlight, you could see the dropout. If there was no atmosphere, it would just go straight like a razor blade, sharp cutoff. But you see how it's bent, and that's because there's an atmosphere. When we flew by and looked back, we saw that Pluto has blue skies, just like the Earth. There's blue skies of Pluto, molecular nitrogen, plus these hazes are preferentially forward scattering, and they're very blue. This is not a fake. This is the real data showing us Pluto has blue skies. And let me just finish by saying that, instead of having that Hubble portrait where you just had these little pinpoints of light, now we have this beautiful view of the Pluto family with everything being resolved. I didn't really have a chance to talk about Charon, which is half the size of Pluto. It's a remarkable system, actually, Pluto-Charon system. It's the only one known in the solar system where the center of mass of the two objects is actually in the space between the two. Charon, if you look at this, it has two huge features. There's this chasm which dwarfs the Grand Canyon in the United States. It goes 6 kilometers deep, almost encircling Charon, that we think is a remnant of during the 4.6 billion years ago, when it was still warm. You had a lot of water, ice. You had a lot of water, and then as it cooled down and froze. And as you know, when you freeze water, it expands, and it split Charon apart, basically. It split it at the seams, and now this red stuff that you see in Charon's pole, that turns out that's the coldest place on Charon, and we think that material is escaping. Molecular nitrogen is molecular methane is escaping from Pluto's atmosphere, depositing on Charon's atmosphere, and causing this dark coloring. We have the resolved, satellites. The satellites are rotating much faster than we expected. Instead of being synchronously rotating with their rotation around Pluto, they're rotating much faster than that, probably because they got hit as they, sometime early by other bodies, sometime early in the solar system's history. And let me just finish by saying that everybody loved Pluto in the summer of 2015, and we had the cover of the New York Times, just a huge number. Pluto was the star of the show. Fortunately, the spacecraft performed beautifully, and there were no problems. But we could never have predicted what we saw here. But one more thing I want to say is just that we're not finished yet. We're still, as I was mentioning earlier, going deeper into the Kuiper belt, and we have one more flyby. It is happening on New Year's Day 2019. Okay, so that's coming up soon, where we're flying by one of a relatively small Kuiper belt object, but it's in a different family of Kuiper belt objects than Pluto, and also different from the family that produces the comets that come into the interior part of the solar system, like Comet Churyumov-Gerasimenko, that was visited by the Rosetta mission. This object, which is currently called 2014 MU69, and we're having a naming contest now, so you go online and you can suggest a name for this object, but it's in what's called the cold classical Kuiper belt. And those objects, we think, have been in their current locations for the entire age of the solar system, probably changed very little, so they give us a window back, our best window back to the 4.6 billion years ago when the solar system first formed, and it may be the most primitive object ever visited by a spacecraft. So with that, I'll end. Thank you.
And we have time for some questions now from this fabulous story way back up in the balcony there. Ursula, can you reach there?
Could you say a bit about what is thought to be inside Pluto? What is the interior like?
Yeah. In fact, the position of Sputnik Planitia, that giant nitrogen ice sheet, is unusual because it's right at along the tidal axis between Pluto and Charon. And one explanation for why it's there is that there was a big impact, it created a basin, but then that wandered because of after the impact. Some of it penetrated deep into Pluto and dredged up some of the deeper Pluto material, creating a gravity anomaly that then polar wandered into the current configuration. But in order for that to happen, there had to be a liquid water ocean underneath. And so the hypothesis is, in fact, that the reason why we have Sputnik Planitia being where it is right now is because Pluto does have a water ice ocean. And it is, even though it's covered by ice on the surface, it's about 65% rocky material, and then 35% of icy material. The density is around 2 grams per cubic centimeter. But other than that, we don't know too much more about the bulk composition underneath.
Question back there.
Robert Klitzman from Columbia, thank you. Why is the angle of the orbit so different, is it thought? And what does that say about our understandings of orbits?
Yeah. Okay. Well, I mean, it's the whole. If you look at the entire Kuiper belt population and look at the statistics of their orbits, the ones that are near, that are just have relatively small inclinations, the ones that are less than 5 degrees, were the ones that I'm calling the cold classical Kuiper belt, and those probably have remained relatively undisturbed since the time of formation of the solar system. But all the others, the 2 other families, including Pluto's family, which are called Plutinos, these are in a 3-to-2 resonance with Neptune. So Neptune is the big gorilla in the room that perturbs the orbits of all the other objects and jacks up their eccentricities and their inclination angles to what we see today. And some of the objects, that third category that produces the comets, are called the scattered Kuiper belt population. So Pluto is one of the Plutinos, and there are several orbital resonances with Pluto throughout, with Neptune in the Kuiper belt as you go from 30 AU out to 50 AU. There's other resonances besides the 3-to-2. The 3-to-2 resonance, by the way, means that every time that Neptune takes 3 times to go around the sun, Pluto goes twice, and all of the Plutinos have to share that same property, and that protects them dynamically, so they're stable over the age of the solar system once they get into that mean motion resonance. But anyway, it's the formation of those different families, though, in the very first place, is what motivated people to hypothesize this radial migration of the giant planets, and that they were more compact within 15 AU instead of going all the way out to 30 in the early times in the solar system. And then, because of the mean motion resonances set up among the giant planets, you then get this evolution to produce what we have today. And it explains, it's called the Nice model. It came out of a conference in Nice, France, in 2005, I think it was. And, they now, it's all, basically Newtonian physics that they can, have put together scenarios. It depends on initial conditions as to what you end up with, but it seems to explain, they call it the theory of everything in terms of planetary formation.
Thank you. Over here, Shapiro.
Erwin Shapiro, Cambridge. Very neat talk.
Thank you.
I'd like to pursue the atmosphere a little bit.
Uh-huh.
How does the surface pressure on Pluto, the atmosphere, compare to the Earth's, and how is it expected to vary over the Pluto year? And lastly, what have you learned of the composition of the atmosphere?
Yes, okay, very good. So the atmosphere is primarily molecular nitrogen, because that's the one that's still active, at those very cold temperatures, and it's about 10 to the minus 5 of bar, so 100,000th of the atmospheric pressure that we have here at the surface of the Earth, with about 0.1% of methane, and then some other simple hydrocarbons, acetylene, ethylene, and other species. And we took an inventory, we did an assay and have all of these different species by that ultraviolet experiment, the solar occultation experiment. We were able to tell the radio occultation experiment that gave us the temperature and the mean mass of the atmosphere as a function of height above the surface. It went all the way down to the surface and mapped both the temperature and the pressure as a function of altitude over Pluto's surface, and we have all that published in our papers already. But it's there were some surprises, but it was we finally got down to the surface and measured the pressure there and the temperature. It's 38 Kelvin at the surface, and the atmosphere is basically in equilibrium, sublimation, condensation, equilibrium with molecular nitrogen ice. Now, Pluto, not only does it have this highly elliptical orbit, but it's also tilted over, and it has some fascinating effects because of the geometry, and going around every 246 years. And our team has looked into that over the age of the solar system. You can go back to several Milankovitch cycles to investigate this. And, it seems to explain, we think we can explain the overall picture of what we're seeing on Pluto now.
Thank you. Question over here.
Joe Taylor from Princeton. I guess the number density of objects in the Kuiper belt is pretty low. And in the 14 months or so between now and when you fly by this object on New Year's Day 2019, and I guess that's a relatively large object because you must know it's already there. But in the meantime, do you go by other things smaller, and are the cameras running in case that happens?
Yeah, you're right that basically space is empty for the most part, but we have looked hard for any objects that are close to the path of the New Horizons spacecraft, and there are a couple of dozen that we pass within 1/10 of an AU or so from, and that we are observing. We've already observed 10 or 15 of them actually, so that we can observe them in geometries that you can't reach from the Earth. Whenever you look at it from the Earth, you're always looking at very low phase angles, and so we are able to observe those at very high phase angles. They tell us something about the surfaces of those bodies, and also we can tell better than you can from Hubble whether or not they're multiple objects, because there seem to be lots of binaries in the Kuiper belt. But that object that we're flying by, it's not so big. It's only 30 kilometers across, we think, okay? And it was very hard to find. We spent several years using the largest telescopes on the Earth, because with the statistics we thought we knew about the Kuiper belt 5 years ago, we predicted that we would have a relatively not easy, but using the largest telescopes on Earth, we could find an object that the New Horizons spacecraft could fly by. But it turned out that first of all, because the direction we were looking was in Sagittarius, which is so dense with stars, it was like picking out a needle in a haystack. It was very hard to do, and we didn't succeed. And we were getting close to the Pluto encounter, and we realized, well, you can't just discover it. You have to map its orbit so that you can now fly the spacecraft next to it. And so we put on a massive press and went to Hubble Space Telescope and submitted a huge proposal to do a deep search with Hubble, and that's saved us. It was in the summer of 2014 that we spent nearly 200 orbits of Hubble time to find this object that we're flying by. Because it had to be reached by the amount of fuel we had on the spacecraft. We had these little hydrazine thrusters to do the trajectory correction, but we can only go plus or minus 1 degree about the trajectory. So we had to find an object in this little cone that was, in space, and have the object being at that place at the right time when we fly by. That's the only. So, and in terms of, the velocity difference that you had to produce is, we had to look for something that was less than 150 meters per second, delta V, to be able to get there. And we found something that was about 60 meters per second. And all the rest, we found, like a handful of others, but they weren't close enough. So, that's, we just feel really lucky that we found this one object, and it had to be in one of what's called the cold classical region.